Hi everyone, I hope you're enjoying the clinic so far. Today we'll be doing a session called Introduction to Model Implementation. And I will be showing you how to implement a simplified version of the ordinary differential equation SIR model that Steve in his lecture and then Zintle in the summary discussed with you yesterday. And we'll be doing this implementation in R. I'll be showing you how to get from these equations to these epidemic curves. And to make things simpler for this session, we'll be thinking in terms of ordering difference equations instead of differential equations, meaning that the dt in these equations are not infinitesimally small, but we'll be thinking in terms of units of days. Let's open our session. So we'll start by writing down these rates of change in these equations. And we write them easily readable. So we say the change in the susceptibles is minus beta times S times I divided by N. Right, didn't forget anything. So the rate of change in the susceptibles is minus the transmission coefficient times the number of susceptible people times the prevalence of the infection in the entire population. The rate of change in the infected group will be everyone coming in from the susceptible group minus everyone who recovers. And we say that the rate of the recovery is gamma times the number of infecteds. Okay, so we still match up with these equations. And then we say the rate of change in the recovered group is all those who recover. Okay, so these equations form the basis of the SIR model, and we will be using them over and over as we go from the equations to epidemic curves. So over time, so let's make a function that can run these equations. And it's always good to make comments of what you're busy with. So let's say this function calculates the rate of change in each state variable. And say, let's call this function change. And we say it's a function, and we wrap it in curly brackets. And this function, the arguments of this function will be the state variables. So the values that are returned from this function will depend on the state variables that we give it. So let's make this a vector called x, and then we say, so S is the first element of x, I is the second element of x, and R is the third element of x. Okay, so we change.dt is a function of x. It's also a function of beta and of gamma. So for this function, we'll be able to change these parameters and input variables. Okay, so does this function capture everything on this slide? Oh, one more thing. We mentioned n there, but we didn't define n. But of course, this is a closed population. We're running the SIR model without births and deaths. So the total population size is just S plus I plus R. Okay, so everything we use here are now defined somewhere, and then we want this function to return for us these values that we just calculated. So the rate of change in the susceptibles, the rate of change in the infecteds, and the rate of change in the recovereds. Okay, so let's run this function. And let's use a small example. So let's see, we run this and let's define X. X is, let's say we have a total population of 5,000 people. At this time point, whenever that is, there are 4,500 people susceptible and 100 are infected and 400 are recovered. And let's define beta as 0.2 and gamma as, let's say this infection has a duration of 50 days. Gamma is 1/50. So let's see in this system at this time point, what would have been the rate of change in each of the state variables. So the number of susceptibles would have reduced by 19.1. The number of infecteds would have increased by 17, and 2 people would have recovered. Okay. So now that was for one time period. And since we didn't define that yet, but let's use, like in Steve's lecture, the units of per day. And we define beta as the contact rate or the transmission coefficient, which is the contact rate per day times the infectivity. And the duration of the infection is 50 days. So this change in the system would have been a per day change. So we now want to run this epidemic over time. Let's write another function that will update our system at each time step. So let's call this function updates the system at each time step. And why I'm saying time step and not day, like I talked about earlier, we don't have to run it in time steps of a day. We can choose smaller time steps. So this function we'll call update the system. And we will update the system at each time step with these values, the rates of change. And therefore, we will definitely be using this function change dt inside this function somewhere, right? Change.dt. And change.dt has these arguments. It's the values of the system at the time, so the values of S, I, and R, and the beta parameter and the gamma parameter. So this update system function will definitely also need these same arguments, beta and gamma. Same arguments that this function requires. And what this system has to do for us, it needs to take the values of the system at the beginning of the time step, and it needs to update it with the changes in the system. And it will update our system for us to new values. So the old values of the system, the old values of S, I, and R will be replaced by the values at the end of the time step. And like I said earlier, these are now in units of per day, but we don't have to do that. We can have smaller time steps. And that would mean we'll just multiply the changes per day by delta t. And delta t, it will also have to be an argument, and we can define delta t as fractions of a day. Okay, so this system will take, this function will take the system at the beginning, update it with the changes we make per the time step, and it will return the values of the updated system. Okay, so let's see. Let's run this function. And we remember our values we had earlier. So let's use them again. And we say update system. And let's use the same values. And let's for the moment say delta t equals 1. So we keep it in units of 1 day. And let's run that. So we started off with 4,500 in the susceptible compartment, 100 in the infectious compartment, and 400 in the recovered. And then we added to that system these values that we calculated here. So let's just, for our sanity, calculate that. Minus 19. And we see it's the same value. So our system at the beginning of the time step was updated by the values that we worked out here. Okay, so you can see where this is going. Okay, so now let's make some decisions. We want to be able to play with our parameters, and we want to be able to play with what the system looks like at the beginning. So let's make some definitions. And we define early on the things that we want to tweak. So let's say, how many people are in S, I, and R at time equals 0. So let's call that system at the beginning, sys is, and let's stick with the 5,000 people in total, and let's say at time 0, 5 people are infected and no one has recovered yet. Let's define beta, no, the transmission coefficient. We call that beta, what did we said 0.2. And the recovery rate, comma, sorry, I want to stay consistent with my coding, and gamma is 1/50. And let's define our time step. And let's say we are now thinking in terms of half days. Okay. Let's run it. So this is our system at time 0, our parameters, and our time steps. And now we will run our system for time in look back to that. So we want to run the system from time 0 up to, okay, let's also define that as the duration of, no, I shouldn't call it the duration of the epidemics. Let's just call it the time period. And we say period equals 365 days. So we want to update the system from time 0 up to 365 days sequence. So this function will create a vector of all the time steps from time delta t up to 365. So we won't start at time 0 because we already have the values of the system at time 0. We defined that. So we start at time 0 plus 1 time step, which is delta t. And this function sequence says from delta t to period by time steps delta t. Let's quickly run this so that we can see. I use the shortcut Control Enter, or you can just say run. Oopsie, I haven't defined that yet. See, so this creates a vector from 0.5 up to 365 in time steps of half a day. So for each of these times, we want to update our system. So we started with the system at time 0, right? And at the end of the time step, we want to have the new values of the system. So system equals the system, the updated system of the system at the beginning with the parameters beta, gamma, and delta t. Okay. But this means that the system will be updated at every time step. It won't keep record of what's happening. So let's create a data frame, and let's call it epidemic. And we create this to represent at time 0 what the epidemic looks like. So let's give it a variable called time, and we know at time 0 that's just 0. And S equals sys, the first element, I equals sys, second element, and R equals sys, the third element. Okay, let's run that and let's see. So epidemic is a data frame that we started at time 0, all the values of the system at time 0. And then we will want to, each time we update the system, add a row to this data frame. So epidemic will be binding rows together of this old data frame epidemic. And we will bind below the previous time steps data frame the time point that we are in and the values of system. Okay. So let's see. Let's just make sure that system is at the beginning, time 0, just defined epidemic. So epidemic has one row, and let's update the system from time delta t to a year. Goes very quickly. And now let's see what epidemic looks like. So we see as time goes by, how the system changes. And after a year, we can see almost no one left in the susceptibles. There are 8 infected people, and almost everyone. The rest are in the recovered state. So I promised you that we will draw epidemic curves. So let's, I use ggplot. So first let's load the tidyverse library. And ggplot likes data frames that are in long format. So let's quickly transform the data frame epidemic. And we'll use this function pivot longer that takes data from wide format to long format. And the 3 variables that we want underneath each other are S, I, and R. So we're asking to take these 3 variables. We say that the values should now be called counts. Why did my R freeze? There we go. Counts, and the names will now be called states. Let's quickly run this. So ggEpi is now in long format. So at each time point, we have the values for S, I, and R below each other. And then we'll say ggplot. I'll just make a very simple plot. ggplot this data frame, and we're going to make a line plot where x equals time, y equals counts, and the colors of the lines equals state. Let's see. And there you go. Here we have our epidemic curves. So you all are very welcome to play around with this code, see how changes in the parameters affect the curves. I will save this code and upload it. It will be on the schedule. So please download it and play around with it as you need. Okay, thank you. Bye.